So we'll be looking to understand the relationship between the reaction mechanism and the balanced chemical equation. We're actually going to start seeing the places where sometimes the balanced chemical equation can have some relationship to the chemical equation, to the reaction mechanism. We'll be looking at predicting the rate law given an elementary mechanism, and predict the rate law given, in some cases, more complicated mechanisms. For reaction, the reaction mechanism is a series of elementary steps, discrete molecular interaction events. Molecule one collides with molecule two, molecule one sticks to a surface, by which a chemical reaction actually proceeds. The balanced chemical equation has the start and the end, but not necessarily any of the steps in between. There's no rule saying it has to be one step. In fact, in most cases, there's a lot of steps involved. So the elementary steps do add up to give the net balanced equation. First one thing happens, then the next thing happens, and the next thing happens. And if you chain all those together, if you sum what happens in each of those steps, then you will start with the reactants and end with the products. So what information is contained in the reaction mechanism that isn't in the net balanced chemical equation? Which specific bonds are broken and formed in which order? If we start with some molecules and then in different molecules, we have to break some bonds and form some more bonds, and they don't all just magically happen at once. They usually happen in some concerted order. Shows how electrons and atoms are transferred between molecules. Where the electrons end up might not be where they might not have jumped from one place to the next place directly. They might have gone through some more circuitous route, but with an easier route for the electrons to travel. And shows the relative speed of each elementary step. Not all the steps happen at the same speed. They happen at different speeds. And the order, right? You've got all the different steps. Obviously, the mechanism is going to say what happens first, then what happens next. So a reaction mechanism, we said, it's the series of elementary steps by which a chemical reaction actually proceeds. So what are some common types of elementary reaction? A given bond breaks within a molecule. Maybe that there's some jiggling that's going on within the molecule. The kinetic energy is going on. Eventually, one molecule happens to have enough kinetic energy that it shakes loose one of the bonds and that bond breaks. Two molecules collide, providing energy to trigger a reaction, or a molecule binding to the surface. These are all common types of distinct elementary reactions that could happen. Why do we care about the reaction mechanism? This is important. It's in a lot of cases, it's very important to know the reaction mechanism if we want to, for example, control the reaction outcome. We want to know which of the steps is the slowest. So, if we're working on some chemical process, we can speed it up, or we can inhibit it if we don't want it to happen, like rust. You want to be able to figure out what's the step that's causing the rust, and then add some coating or something to stop that from happening. So if we know the information about what the reaction mechanism is going on, we could develop a new related reaction. We could understand how to make more of a new compound because this will probably undergo a similar reaction as that, and therefore we can put it under these conditions. Or it differs in this way, and therefore the reaction mechanism will likely be different in this way, and we can do something else in order to make it happen fast. That's frequently what you're interested in chemical processes, figuring out how to get the reaction to go a lot faster than you thought it was going to. Okay, so that's why we're interested. So let's take a look at some of these reaction mechanisms. So let's just compare the net reaction. So a net reaction, in this case, for making chloroform carbon tetrachloride might involve reacting trichloromethane with chlorine. And that's the net reaction, but the actual reaction is much more complicated. You might have a fast step of chlorine breaking apart into two chlorine ions, and then the slow step where the chlorine ion, you can have species in here that are not Lewis structure stable because they only exist for a short amount of time. And then you would have the chlorine interact with the trichloromethane and kick off and pull off a hydrogen, and then now to make a stable species, but now you've got this unstable trichloromethane ion, or it's not even trichloromethane ion, it's trichloromethane minus a hydrogen. And then you have one of the chlorine atoms around interacting with the trichloromethane. We only have one electron that's a radical. The two radicals combined to form carbon tetrachloride. And so those are the complicated reactions that actually go on in this. Many complicated steps going on, a lot of times creating unstable species, but the net reaction just is what we saw at the beginning. So that is usually what we're interested in. Reaction mechanisms can be very complicated. So some terminology, chlorine alone, I might have said chlorine ion before, I can't remember, but it's just chlorine alone, the chlorine radical and the carbon trichloride radical are called reaction intermediates because they're transient reactive species. They're usually not ones that are particularly stable, that are formed in one step and then consumed in another, so they don't appear in the net overall reaction. And an important point here, the key point is that the slowest step in the mechanism is called the rate limiting or rate determining step, which is step 2 here. And that's very important because that's the step that determines the overall rate of the reaction, right? If 2 of the steps are fast, the first step just happens very quickly, and then just these chlorine radicals are sitting around waiting to be able to have a chance to pull a hydrogen off the trichloromethane. So it's not really determined by that first step. And then once the slow step happens, then the third step happens quickly. So really that's what you want to be looking for in the mechanism, what the rate determining step is. Because the overall reaction cannot go any faster than that rate determining step. And the rate of reaction is, once you go through the math, and we'll see the examples in some of these processes, it's going to be limited by that rate limiting step. That is what is going to determine the overall kinetics. Okay, some more important terminology here, understanding some of the one-step reactions. So if the reaction is indeed an elementary one-step reaction, then the coefficients in the balanced equation of that elementary one-step reaction are indeed the reaction order and the rate law. So before we said, no, the stoichiometric coefficients don't necessarily have anything to do with the reaction order. Well, there are some cases when they do. In the rare cases where the reaction really is a one-step simple reaction, then yeah, they are. For example, if the elementary step is just A breaking apart, then we call this a unimolecular reaction, and the rate law would be just proportional to the concentration of A, because if there's just one step with A doing something, then the rate will be just proportional to the concentration of A. If there's more A, you're going to get more reaction. If you have an elementary step that is A plus A, then it's bimolecular, and the rate will be proportional to Ka squared. A common example here would be if you have 2 gas molecules colliding together, like hydrogen iodide colliding to create hydrogen and iodine gas, then that is an example of a bimolecular reaction with rate is equal to K times A squared, concentration of A squared. AB is also bimolecular. The rate is going to be proportional to A times B. Again, this is usually the case in gas reactions where the probability of 2 things colliding is just going to be proportional to the density squared. If there's twice as much A, there's twice as many collisions. If there's twice as much B, there's twice as many collisions. If there's twice as much A and twice as much B, there's 4 times as many collisions. That's the basic the basic argument that works. A unimolecular example, radioactive decay. That's something that has a first order rate, and you get decay as an exponential, as we saw in the previous segment. Decomposition of N2O4 to 2NO2. A bimolecular example, again, many reactions in gas that involve collisions between molecules that are only one step. So those are some of the simple one-step elementary reactions that one could see.